All right, class, welcome to my office. Lots of cool decorations. You can see my Serenity comics on this side. You can see the picture I drew in a group meeting the other day of a bus and some other artwork and other various things on my shelves, like some Star Wars stuff. Anyway, class C. So let me share my screen. Yes, I am recording, share my screen. So here's what we're doing in class C today. We are going to talk about parallel and perpendicular lines, how to tell when lines are parallel or when lines are perpendicular without having to graph them, although we will graph some of them. I know there's things in my way, but that's how it is. And then how to use info about parallel or perpendicular lines to find the equation of a different line. And lastly, we'll look at some special cases as well, because there are a couple special cases of parallel and perpendicular lines. So let's look at parallel first. And here's some examples. So here are three equations of lines: y equal to 2x plus 5, y equal to 2x minus 4, and 6x minus 3y equal to 3, that all end up being parallel. Let's actually graph them first just to see that before we kind of identify what makes them parallel. So I'm going to do the tried and true method of just finding the x and y intercepts. So this graph here, I'm just going to write them down. I'm not going to actually work it out. This one here, the y-intercept would be 0, 5. Because if I set x equal to 0, I get y equal to 5. And the x-intercept would be, well, if I set x equal to 0, sorry, if I set y equal to 0, if I subtract 5, I have negative 5 equal to 2x, divided by 2, negative 5 halves, or I will use decimal, negative 2.5 comma 0 is the x-intercept. Similarly here for y equal to 2x minus 4, if I set x equal to 0, I get y equal to negative 4. So 0, negative 4. Remember, that is an x coordinate first, a y coordinate second. That's my y-intercept, right? Because it's on the y-axis because x is 0. My x-intercept here would be, well, if I set y equal to 0, I have 0 equal to 2x minus 4, or adding 4 to both sides, positive 4 equal to 2x, and divided by 2, 2 equals x. So I get x equals 2, so I get the point 2 comma 0. Remember, that's from setting y equal to 0 and getting x equal to 2. Lastly here, I'll show my work here, why not? If I set x equal to 0, I get 6 times 0, let's write that, 6 times 0 minus 3 times y equal to 3. So I have negative 3y equal to 3, divide both sides by negative 3, and y is 3 over negative 3, which is negative 1. Similarly, if I set y equal to 0, I get 6x minus 0, if you like, equal to 3. Did I make a mistake here? No, I don't think so. Just getting worried. Yeah, I'm fine. Yeah. If I did, I'll just start over. So then I've got 6x equal to 3. I've got x equal to positive 1/2, because 3 divided by 6 is 1/2. So my x-intercept is going to be 1/2 comma 0. My y-intercept was 0, negative 1. Cool. Let's graph them. And I'll use some different colors here because I have different colors and I might as well use. So I'm graphing this first one, y equals 2x plus 5. I've got my y-intercept of 0, 5. My x-intercept of negative 2.50. I'm really going to cheat and use negative 1, 1. Negative 2, 1. Apologies. So graphing that line there, it's going to look like that. There's my line with arrows at the end, as we should put for any line. So there's the first line. And then my second line in red is y equals 2x minus 4, x-intercept of 2, y-intercept of negative 4, graphing that line. And hopefully I will draw it well enough that we can like actually see that it looks like it's parallel. Those look pretty parallel. Meaning if you continue them on forever and ever and ever, they would never intersect, at least in the Euclidean geometry sense. There's other geometries where parallel lines intersect. It's weird. Don't worry about it. And then finally, 6x minus 3y equals 3. So if I plot the point x equals negative 1, x equals 0, y equals negative 1. And I should use green. Oh, well. And x equals 1/2, y equals 0. So if I do that, and I'm going to have to be super careful here to make sure this comes out to be looking parallel here. Yeah, close enough. So aside from my potential, not drawing things perfectly, these lines do look parallel. And now what you can see for the lines written in the standard y equals mx plus b slope intercept form, the slope just determines the parallelness. So if you can see that the slopes are the same, which they are here, both of these have a slope of 2, then you can see that those lines are parallel without actually having to graph them. This other line here, though, it's not immediately obvious from the way this equation is written what the slope is. So we could graph it to see that the parallel, or if you want to see that this line was parallel without having to graph it, you could take that equation 6x minus 3y equal to 3 and solve for y. So 6x minus 3y equal to 3. I'm going to subtract 6x from both sides. So I'm going to get negative 3y equal to negative 6x plus 3. And I'm going to divide everything by negative 3. So dividing by negative 3, I get negative 3 divided by negative 3 is 1. Negative 6 divided by negative 3, oh, you can't see that. Negative 6 divided by negative 3 is positive 2. And 3 divided by negative 3 is negative 1. So I get the line y equals 2x minus 1, which is the same as this line here, just written in a different form. And notably, this line also has a slope of 2. So generally we say that lines are parallel if they have the same slope or equal slopes. Okay, so parallel lines, same slope. If they don't have the same slope, they're not parallel. Let's look at the other thing. Let's look at perpendicular lines. I've got some examples for that as well. So here are some lines that will turn out to be perpendicular. So let's graph them again. Y equals 2x plus 5. I just used again because I was feeling lazy. So here's y equals 2x plus 5. It has a y-intercept of 5 and an x-intercept of negative 2.5 or negative 5 halves. So if I graph those points here, once again, again, really cheating and trying to make sure I go through that point there. There's that first line. Whoops. And I'm going to say something more here in a second. And then for my second line, which let's use green, y equals negative 1/2 x plus 1. If I set y equal to 0, well, sorry, if I set x equal to 0, apologies, wrong words there. So that x equal to 0, that's the x coordinate. I'm going to get 0 plus 1 for y, so 1 for y. I set y equal to 0. Let's see, so then 0 equals negative 1/2 x plus 1. I like to make things positive if I can, so I'm going to add a 1/2 x to both sides. So 1/2 x equals 1, and then multiply both sides by 2 to get x equal to 2. So 2 comma 0 is my x-intercept. So 2, 0, 0, 1. I'm going to try and draw these. Let's make it look super perpendicular here. Yeah, let's line that up. Looking good. All right. Awesome. And those lines certainly look perpendicular, and they are perpendicular. And kind of one thing I like to think about here is for the black line, the slope is 2. So I go over 1 and up 2, right? 1, 2. Whereas for the green line, the slope is negative 1/2. I go over 2 and down 1. But those slopes are perpendicular to each other. When you go over and up versus the opposite amount over and down, they end up being perpendicular, which is kind of cool. So there's a couple ways of saying the lines are perpendicular. So we say that lines are perpendicular. Let's call them lines L1 and L2 are perpendicular if there's two different ways of saying this. One way of saying this is if their slopes are opposite inverses, meaning if the slope of line 2 is the negative reciprocal of the slope of line 1, or the slope of line 1 is the negative reciprocal of the slope of line 2. Another equivalent way of saying this is if the product of the slopes of line 1 and line 2 is equal to negative 1. So here for sure we see that, oh yeah, 2 and negative 1/2, they are opposite signs and they are reciprocals, right? 1/2 is the reciprocal of 2, negative 1/2 is the reciprocal of 2 that is the opposite sign of 2. Or you could say that 2 times negative 1/2 does in fact equal negative 1. So if the product of two slopes is equal to negative 1, that means those lines are perpendicular to each other. That's kind of it as far as determining whether or not lines are parallel or perpendicular. Let's look at a couple of examples and then we'll talk about a few more things. So, sorry, grab some paper here. 1 second. Get my notes out of the way here. So page 3, I'm going to try and keep track of the page number 0. Right there, back here. So for example, y equal to 3/7 x plus 1 and y equal to -7/3 x minus 15 definitely are perpendicular. Because 3/7 and -7/3 are opposite inverses, or if you prefer, 3/7 times -7/3 is equal to -1. Or for example, let's actually look at the example. So what about the following two lines? So the question will probably be phrased as, are the following lines parallel, perpendicular, or neither? So what about the lines L1 given by y equal to, sure, 3/2 x plus 1, and line 2 given in not the standard way. Let's do it as, I don't know, 4y minus 6x equal to 5. So line 2. For line 1, we already know what the slope is. I'm going to write that the slope for line 1, which I'm going to call M1 because that feels convenient, is 3/2. Let's find the slope for M2. And the easiest way to find the slope for the other line is to write it in the other form, meaning to solve for y. So I'm going to write this as 4y equal to positive 6x plus 5. And I'm going to divide everything by 4. So 4y divided by 4 equals 6x divided by 4 equals 5 plus, oh my goodness, 5 divided by 4. I don't actually care what's going on over here. This does not affect the parallelness or the perpendicularness whatsoever. So I'm really just going to focus on this. 4y divided by 4 is, of course, y. 6 divided by 4 reduces to 3/2. And even if this reduced, I would probably just not even write anything here, to be perfectly honest. But sure, I can leave that as 5/4 or 1.25 per decimal. So M2 is 3/2, and these lines are parallel. I should have written perpendicular, perpendicular, because the slopes are equal. M1 is equal to M2. On the other hand, there's lots of situations where lines are neither. For example, if I had the lines, I don't know, y equal to 2x plus 3 and y equal to -2x minus 7, well, the slopes definitely aren't equal, right? M1 is 2 and M2 is -2, and 2 definitely doesn't equal to -2. And the slopes, while being opposite signs, they are not reciprocals of each other. So, right, 2 doesn't equal the negative of 1 over -2. I don't love doing it that way. That just feels cumbersome to me. Like, I don't want to check that M1 doesn't equal -1 over M2. I think it's actually typically more convenient to just check that, oh yeah, M1 times M2, which is equal to 2 times -2, is -4. But for them to be perpendicular, that product has to be equal to -1. And that's not equal to -1. So we can see that from here, they're not parallel. And from here, they're not perpendicular. We often use this symbol for perpendicular because perpendicular is just a long word to write out. So we can say that these lines are neither parallel nor perpendicular, which kind of feels like a mouthful, but whatever. Yeah. So really, I mean, checking the lines are parallel or perpendicular. One, you want to write the line in the standard slope intercept form so that it's easy to tell what the slope is. And then after that, you just have to compare the slopes. Are the two slopes the same, or are they multiplying to -1? If neither of those things are true, they're neither parallel nor perpendicular. Let's do one more example, and then we will move on to finding some equations of lines. So let's do the following. Are these lines parallel perpendicular, or neither. And before I do this question, you should pause the video and try and do it yourself. So let's say we have the lines L1 given by I'm going to do it, sure, I'll do it this way. 2x minus 5y equal to 7, and line 2 given by, now I have to think about what it's supposed to be here, y equal to negative 5 halves x plus 1. So let's find out. So this one, we certainly know that the slope for line 2 is just negative 5 halves, or if you like a decimal, negative 2.5. Over here, we have to solve for y. So 2x minus 5y, I don't know why I'm writing the same equation again. I could have done a step. I could have subtracted 2x from both sides. So negative 5y equals negative 2x plus 7. And then divide everything by negative 5. Negative 5 divided by negative 5 is 1, but the y sticks around, right? The y doesn't go away. So I get 1 times y, which is just y. Negative 2 divided by negative 5 is a positive 2/5 x minus 7/5. So I can see that M1, the slope for the first line, is positive 2/5. Or if you like a decimal, 2 divided by 4 is 2 divided by 5 is 0.4. Writing it in my terms, writing it as a decimal doesn't really help me see whether they're parallel or perpendicular, but you might like a decimal. So here you can observe, well, 2/5 and negative 5 halves are opposite signs and reciprocals. So we can say that or I really should say that not that M1 is perpendicular to M2, but L1 is perpendicular to L2. Because, I don't know, 2/5 is the negative reciprocal of negative 5 halves. That just feels, I don't love writing it that way. You can write it that way if you want, or you can just be like, because my slopes are, because M1 is 2/5 and M2 is negative 5 halves. But I really, really, really have to admit, I feel like the easiest way to kind of justify my reasoning here is to say because M1 times M2 is equal to 2/5 times negative 5 halves, and that equals negative 1. So even though I didn't think I liked doing it that way, that's actually the way I think I prefer doing it. Such is life. You learn new things about yourself all the time. So let's move on to using these things to find some equations of lines. Yeah, new page. So we'll do like 3 or 4 examples here. How much time have I got? It doesn't show me how much time I've used on this thing. That's annoying, but yeah, that's annoying. Oh, well, I'll just have to guess. So let's see here. Let's find the equation of the line parallel to y equals 3x plus 1 that passes through the point, or passing through the point, (2, 4). So the whole point, pun, not really a pun was intended. Not really a pun though, right? I'm just using the word point. The whole point of this is that we have to know, to find the equation of the line, 2 pieces of information. We need a point, which we have, and we need a slope, which we can discern from this equation here. So our slope is going to be 3, because our line is parallel to that line. And our point is going to be 2, 4. And I'm going to do it the point slope way, which is saying my equation is going to be given by y minus the y coordinate equal to the slope times x minus the x coordinate. And then I solve for y. So y minus 4 equals 3x minus 6, just distributing the 3 there. And then adding 4 to both sides, I get y equal to 3x minus 6 plus 4 is minus 2. That's the equation of my parallel line. This line is definitely parallel to that line. They have the same slope. And if I plugged in the point 2, 4, it would work, right? If I plug in 2 for x, 3 times 2 is 6, 6 minus 2 is 4. Let's continue with this example. Sorry, that threw those hands there. Let's go ahead and also find the line perpendicular to y equals 3x plus 1, also passing through the point 2, 4. Word of warning, the answer here is not going to be y equal to negative 1/3 x minus 2. Even though the slope is negative 1/3, the y-intercept isn't going to be the same, right? If we think about this line here, y equals 3x minus 2 looks something like, I have to kind of try and graph it here. It's got a y-intercept of -2. It passes the point 2, 4. Looks kind of like this. X is 2. And then the perpendicular line that I'm about to try and find the equation of is going to look something like this. And you can see from the graph, the y-intercept is going to be much larger than -2. It might be like +5 or +6 or some fractional number in between. So we can't just use the same y-intercept. So not that. Instead, we're going to do the same process. We're going to say, well, now our slope is going to be, instead of +3, our slope is going to be negative 1/3. Our point is still 2, 4. I can apply the same methodology. I'm going to say y minus the y coordinate equals negative 1/3 times x minus the x coordinate. Here things are going to be a little bit messier. I'm going to have y minus 4 equal to negative 1/3 x, and negative 1/3 times -2 is positive 2/3. I'm going to add 4 to both sides, but I'm also going to change it to having a common denominator. So I know that 4 over 1 times 3 over 3 is 12 over 3. So I'm going to add 4, but I'm going to write it as 12 over 3. So y is going to equal negative 1/3 x plus 2/3 plus 4, which is 12 over 3. And then I'm going to get 4 2/3, which is going to be 14/3, which is the better. I don't think it's actually better. I think it's the preferred way of writing it. So even though 4 2/3 is more informative as far as where this point actually lives here, writing it as 14/3 is the more standard way of doing it. So there's our line that is perpendicular to y equals 3x plus 1 and passing point 2, 4. Let's do one more example where we do both of these, and then we'll talk about some special cases. So that was 4, 5. So similar idea. We'll do both parallel and perpendicular. So let's say I want to find the equation of the line parallel to, how gross do I want this to be? Not that gross. Let's make it, sure, 5x plus, sure, 4y equal to 20, just to make it nice. Parallel to that, passing through the point. Does need to be a point that's not on this graph. So let's make it the point, I don't know, 1, 2. So first and foremost, we have to find the slope if we're trying to find the slope, the equation of a parallel line. Well, I don't see the slope easily. I want to emphasize here the slope is not 5. It's not the coefficient of x unless the equation of the line is written in the standard slope intercept form. So I'm going to do that. I'm going to say, well, 5x plus 4y equals 20, subtract 5x, 4y equals negative 5x plus 20, and then divide both sides by 4. So y equals negative 5 over 4x plus 20 divided by 4 is 5. Again, I don't actually care about this number here, but I'm not going to do the wrong thing. So then we know that our slope is negative 5/4, and our point is 1, 2. And instead of doing it the way I like to do it, I'll do it the other way just to kind of show the usual thing. So you could do it y minus 2 equals negative 5/4 times x minus 1. I'm going to do it as y equals negative 5/4 x plus b, and I'm going to plug in the point. I'm going to plug that in and get 2 equals negative 5/4 times 1 plus b. So then 2 equals negative 5/4 plus b, adding 5/4. 2 I'm going to rewrite as the fraction 8/4. I'm multiplying 2/1 by 4/4. I'm adding 5/4 to both sides. So b is going to be 13/4. So the equation of this line is y equal to negative 5/4 x plus 13/4. Let's find the equation of the line that's perpendicular. So perpendicular line, perpendicular line to the above equation, passing through the same point. So the only thing that's going to change really for us is instead of our slope being negative 5/4, now our slope is going to be positive 4/5. Our point is still 1, 2, and I'm going to do it the way I prefer to do it this time. So my equation is going to be given by y minus the y coordinate equals my slope times x minus the x coordinate. Then I'm going to solve for y. So y minus 2 equals 4/5 x minus 4/5 times 1 is just 4/5. Right? I'm just distributing the 4/5 there. I'm going to add 2 to both sides. So y equals 4/5 x minus 4/5 plus 2. I should have changed that to a common denominator. 2 is really 2/1 times 5/5 is 10/5. So I really have y equal to 4/5 x minus 4/5 plus 10/5. And negative 4 plus 10 is 6. So negative 4/5 plus 10/5 is 6/5. So that's pretty much all there is to parallel and perpendicular lines. Parallel lines have the same slope. Perpendicular lines have opposite inverse slopes or slopes that multiply to -1. There is kind of 1 or 2 special cases though that I should talk about. So specifically, let's talk about parallel lines first. So parallel lines special case. These lines are parallel. X equals 3 and x equals -2. They're both vertical lines. They are parallel. Right, if I graph them, do my best job here. Here's x equals +3 over here. Right, where, okay, sorry, 1, 2, 3, 2, and here's x equals -2 over here. The thing that makes this a special case is that we can't actually say that these lines have the same slope because their slopes are undefined. So both x equals 3 and x equals -2 have undefined slopes. And it is not correct to say that the undefined slope here is equal to the undefined slope here. We can't say the two undefined things are equal to each other. It's just not how it's done in mathematics. So we just say, oh, we know when the lines are vertical that they're parallel to each other. And then there's also, so it's not, but it's not a challenge for horizontal lines, right? Both horizontal lines like y equals 5, and y equals 3, both have the same slope. They both have a slope of 0. So they're definitely parallel in the usual way where both slopes are the same. The other special case is perpendicular lines. So we have a perpendicular line special case. And it also involves a vertical line. Vertical lines are always problems. Perpendicular line special case. So the special case here is, for example, the line x equals 4 and y equals 3. If we graph those, wow, if I can graph that, all right. So let's see. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So here's the line x equals 4. Good old vertical line. And the slope is undefined. And over here is the horizontal line y equals 3. And oops, equals, and the slope is 0. And they're clearly perpendicular to each other, right? They definitely form a right angle with each other. So x equals 4 and y equals 3 are perpendicular. However, they don't meet the usual definition of perpendicularness because, well, you can't say, right, if you try to take, for example, the negative reciprocal of 0, yes, that's undefined, but we can't, again, it's not allowed in math to say, oh, this thing's undefined and this thing's undefined, they're the same. That is really, really not ever true. So we can't say it's true here, even though we would really like to. Instead, we're going to, and also I will point out that you can't say, so, but undefined equal to undefined doesn't work. Is no good. Sorry, my brain's getting a little messy here. Or the alternative way, when you multiply the slopes together, right? If you do 0, the slope of this line, times undefined, the slope of the other line, we definitely can't say that equals -1. You can't use undefined in a normal kind of equation. So here you're stuck. You just have to know that if one line is horizontal and one line is vertical, that they're definitely going to be perpendicular to each other. So those are the perpendicular and parallel special cases. And that's about it for class C. Yeah, I'll see you all later. Hope you enjoyed the video. Bye.